Welcome everyone to the next installment of our First Robotics Competition workshop series. I have heard that there are some First Tech Challenge teams that have also been watching, which is awesome. So our audience is a little bit larger than what we had thought. Tonight, we're really fortunate to have Gordon back with us tonight. He is going to talk about software and how you get started and some of the very basics. So welcome, Gordon. So happy to have you back, and I will turn it over to you.
Okay, thanks, Luann. So yes, this is going to be a little different probably from what you thought it was going to be, because this is going to be a really basic introduction to software and software for FRC, but I hope you'll learn something. I've had a lot of experience in a lot of these areas, and getting over the first hurdle of writing a bit of software or modifying an existing bit of software, I find is a big hurdle for people. And people say to me, how do I write that first bit of code? So I want to step back a little bit to getting you to writing that first bit of code, and we'll actually walk through some code for an FRC robot, and we'll break some of that code, and getting you past the reticence to write that first piece of code and dealing with some of the bugs that you might find, hopefully will be useful. We can do a further seminar later about actually writing more detailed code and so on, but this is just an introduction of how you get into writing software. So I hope it's useful. And with that, I'm going to start presenting, and that just requires me to click a few buttons and hopefully share the right window and then present. And we should be good to go. So this is me. This is me as a referee at FRC competitions, which I've done for a number of years. I'm only talking on behalf of myself. These talks are my own views, and you can disagree, and I'd like you to disagree, and I'd like you to tell me where you disagree. Please contact me. And hopefully we'll start some discussions. Hopefully about the talk, whether the talk was useful, how it could be improved, and also what other talks people might be interested in, and whether these spark some ideas in you. So a little bit about me. I'm actually retired. I retired this year. I have a Bachelor of Science in Computer Science with honours many years ago. I worked for about 35 years in the computer industry, and I worked at all sorts of levels. So I wrote machine code, actually putting the bytes into the CPU. I wrote some assembly code, quite a lot of that. I wrote for embedded gear, so actual telco gear, OS firewalls for data switching gear. I wrote on real-time, general purpose, compute farms, wrote in various languages, 4 major languages. And while I worked at Google, which was the last 13 and a bit years of my career, I wrote in over 20 languages. So I've written in a lot of things. And over the last number of years, I've led many teams of software engineers. So I've seen a lot of different issues with writing software, even for skilled software engineers. So hopefully this gives some background of why I'm giving this talk and why it's important for people starting out. You don't just immediately become a proficient software engineer. It takes steps. So why do I want to give this talk? I want to demystify programming a little bit, I hope, because there seems to be this magic of there's the robot and there's the code, and how do these things go together? And how does the code do something to the robot? So I want to step back and say, well, how does code work? Understand a little bit about central processing units, or CPUs, make some of that connection between the code and the robot, and then the very first program that you might want to write to get an FRC robot working. The first thing is programming isn't magic. It's really important to understand the basics. And I think one of the biggest hurdles that people have is someone can write code on the team and everyone else sits back and goes, I don't understand anything about that, so I won't get involved. So hopefully if we can get a little bit further and look at this and go, okay, I understand how code works. Oh, I just need to put that in there and I need to change that a little bit and things work a little differently. We can move over that hurdle that is writing that first piece of code, because there's a lot of extraneous stuff that goes with coding. So I want to talk a bit about that and talk a bit about why that stuff doesn't matter and you can ignore it, but how you ignore it sensibly. The FRC toolkit and all the libraries hide a lot of the complexity of programming a robot, and that's great. That makes it much easier because you just have to put code in certain sections. But it's also bad because you don't understand how the robot is actually doing things. There's magic happens here and a bit more magic happens here and a bit more magic happens here. And hopefully if I put all that magic together, the robot does something. But most importantly, and I have a history of being a tutor and an instructor, I like people to understand why they're doing something. So it's not just a matter of poking stuff into particular holes. I'd like you to understand why you're poking the stuff into holes so that as you go, where do I need to change it? You can go, oh, that's why I'm doing that. And that's what I'm trying to get through with this talk. So let's talk a little bit about central processing units or CPUs. Computers are dumb. And that's the most important thing that I want you to remember from this talk. Computers are dumb. Computers do what they tell you to do. And because humans are relatively smart, but easily forget things and get things wrong, we can tell computers to do the wrong thing very easily. It's harder for us to tell computers to do the right thing. But let's actually put some methodology into this and do things in a systematic way, which makes it easier for us to tell the computers what to do. Remembering that computers are dumb. They won't do what we want them to do. They'll do what we tell them to do. So what does a CPU do? CPUs at its most basic level can do one thing at a time. And I'm ignoring multi-threaded, multi-processor CPUs. I'm talking about what a CPU can do. There are different types of CPUs that can do multiple instructions at one time, but the computers that we're talking about do one thing at a time. At the most basic level, they can get values from a location, which might be part of the CPU or it might be some memory, and they can put values back in locations, which might be part of the CPU, a device attached at a location in memory, or a piece of memory that they store. They can add values together, and subtraction is adding negative values, multiplication is adding many, many values in a loop, but adding is really the fundamental thing. And finally, they can test values and jump somewhere else, execute a different instruction as a result of the test. And yes, there are many, many more things that most CPUs can do, interrupts, multiprocessing, and so on. But these are the fundamental operations that a CPU can do. And we write in computer languages that combine and hide these basic steps. So when you write an assignment or a multiplication statement in a higher level language, that's actually instructing the CPU to do a bunch of smaller instructions and put the result back in a memory location. So what does do one thing at a time mean? Typically, programs have a main loop, and the FRC robot system has a main loop. It's hidden, but it's there. It runs forever. Its job is just to sit there going, I need to go and dispatch other bits of code. So I run around a loop and just say, do this, do this, do this, do this, start again, do this, do this, do this, do this, start again. That's all it does until it's interrupted by some method of interruption, like the CPU is turned off, or what's called a watchdog goes off that says you can't run for any longer. And we'll talk a little bit about that. The main loop behind the scenes, and this is where the code hides things from you that are important, but you don't need to worry about. Things like field communication. Once your radio's set up, the FRC libraries actually ensure that you can communicate with the field, that you can read input, you can drive motors. You don't care exactly how that works. You have subroutines or, excuse me, library routines that you can call to do this work, but it's all hidden behind, which is great because you can focus on what you want to do. You want to drive a robot, you want to lift an arm, you want to catch a ball, and so on. And then the main loop calls some predefined functions, and we'll talk about these functions, routines, whatever you'd like to call them. Start the autonomous period, do something periodically during the autonomous period, start the teleop period and do something periodically during the teleop period. And that's fundamentally what the libraries do for you. So your job is to fill out those 4 routines to do the right things that you want to happen in start, during autonomous, start teleop, during teleop. But I want you to remember, and this is really important, and I was talking to someone the other day who said they had finally got it after writing FRC code for a little while, once they'd started doing university courses, that it only looks like things are happening concurrently, because behind the scenes, the library and the processor are doing work that make it look like all of these things are happening at the same time. But actually, if you get the logical sequence, they are running them in order. So getting and putting values, this is the key work of a CPU. Calculations is probably a close second. So you might be reading the value of a sensor. You might be working out how fast the motor is going or where the location of a particular controller is. You might want to set the motor speed. So you might want to push a value or put a value to it. You might want to calculate a result and retrieve them later. And we really have two device types in general. And I'm not talking about how they're connected to the computer, but there are set at a particular value and do that forever, or set at a value and hope that it's right, check that it's right. Is it right? No, it's not right. Try again. They're really the two types of devices you need to deal with. And as you're doing things like driving or turning, you write loops that do an approximation of a circle or an approximation of a turn, and you check to see whether you're doing the right thing. So driving straight is very easy. You just say, I want to do this for this long. Turning a curve is actually much more complex because you have to do maths and check that you're doing that turn correctly. So devices and programs can be smart or dumb, or simple and or more complex. You might want to add values. So add a constant, add an offset, increase something, add values of two memory locations. Why do you want to do that? What's the whole point? Because you want to store values for a later use. You've calculated an offset. Now you want to use it on the next time round the loop. And the most critical function, which makes CPUs useful, is to test a value and do a jump as a result. So is the speed 12 yet? Have we set the motor fast enough to be 12, or is it at 12? Whatever 12 happens to be for this particular motor controller, it doesn't matter what the actual value is. If it is, yes, go and do something else because I've achieved my target. No, just continue on with the next instruction or go around the loop or whatever. And this could be inverted. It depends on the CPU. It doesn't really matter. But fundamentally, all loops resolve to this. So whatever language you're using, whether it's a while loop or a for loop or a do until loop, all of these resolve to test the value 12 and then either loop again or jump somewhere else, depending on how the language is implemented, based on that test. And once you actually get that central idea of what the construct in your language means, like the while loop or the for loop or the do loop, all of those resolve to do something in a loop and add a test somewhere. And when the test succeeds or fails, depending on how it's written, we want to do something else. So why do we care? Why did I go back to the basics? It's really important to think of all of those things that the CPU has to do to achieve your goals. And if I go back to the first step, things look like they're concurrent. What does it mean if things are not concurrent? If you've only got one thread or one set of execution that can happen? If your main loop calls a subroutine to talk to a motor controller, for example, or turn a curve, and you sit in an infinite loop or a very, very long loop in that subroutine, and you never get back to the main loop or don't get back to it fast enough, then the main loop doesn't get time to do the things like talk to the field, and it might actually decide to turn you off. So called functions must return as quickly as reasonable. So be careful with loops. Make sure that they terminate properly. That condition that we talked about on the previous page, make sure that it's correct. If it's not 12 and you put 1200, it's going to do it 100 times as long. That might require your loop to run too long, depending on what needs to happen in the interim. So if you spend too long, the CPU or the management system doesn't get to do the housekeeping. And the way our systems are set up, they eventually get angry and terminate your program because you actually need to talk to the field or talk to controllers or whatever. And eventually you just get shut down. And that's a good thing. These things are obvious, and we'll talk about these common mistakes later, but these are the fundamental things that happen when you're writing code that you go, really, how could I do that? But we do it all the time. If you add the wrong values, the wrong thing happens. That feels like a duh, but that's obvious. But that's the point. Most bugs are obvious. Most bugs, they may not be obvious to find, but once you've found them, you go, oh, really? How could I do that? So if you go back and act like a CPU, act dumb, and you go, oh, I didn't mean to add 3, I meant to add 30, then you can see why the bug exists. If you test the wrong conditions, the code doesn't work. Right? Same thing. If you expected your loop to terminate at 12 and you had 1200, or you had a scaling factor somewhere, or you retrieved a value from the wrong location or with the wrong scale factor, the code does the wrong thing. Now, it's possible, especially with the sort of hardware that we're working with and embedded systems, these are effectively embedded systems, hardware does go wrong, especially if you've got stray line voltages around and things like that. Hardware does weird things, but it's more frequently coding mistakes that's causing the problems. So what's the most important thing here? Take your time, think it through, and importantly for all of the teams, leave time to write and test the code. One of the things I see and I hear when I talk to a lot of teams is the people writing the code never get a chance to spend time with the robot and actually understand how it's working. So the code's rushed at the end. It's one of the key things, if you go back to the first talk that I gave, it's one of the key functions, subgroups of your FRC team of writing and testing the code. So you need to make sure that that's in your schedule as time to write and test the code. And if you change the hardware, you might need to change the code. So it's not fair to change the hardware and say, let's go onto the field. Why isn't the code working with the new hardware? Because you haven't had time to actually design and test it. So common mistakes, and this is where people get tripped up. So all of the ones I just talked about and some others that are really important. And I see these ones all the time. Forgetting to set initial values. You should never, when you're dealing with hardware, never trust the power on state. Always set the value you want, even if it's 0. Actually do an explicit assignment that sets the value to 0 or whatever the default state is. This will save you hours of debugging later. Because once in a million times, once in 1,000 times you turn on that hardware, even though the manufacturer said it starts at value 0, it didn't. These things happen. And once again, if you have a stray voltage that's causing that CPU to be slightly on the edge or that controller to be slightly on the edge and it reads 1.5 instead of 0, things go wrong. So actually take the time to write the initializers, even if it's just set everything to 0. It's also a good methodology to say, what's my startup state? My startup state is this, 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 this. Okay, I know I'm starting from that. Let's go on. Another one that is so easy to do is the loop that I have at the bottom. While the value is less than 12, increment the value. But somewhere along the way, usually hidden within some other lines of code, you've set the value back to 1 or some other value. And every time around the loop, it goes, well, value less than 12, set it to 1, increment it to 2, go back around the loop, and it will go forever. This is an incredibly easy thing to do. It looks really, really obvious and really, really stupid on this slide. But if you added another 20 lines of code around it and you suddenly hide the initializer behind some other things or cover it in some comments or accidentally comment something out, then it's really easy to make this sort of mistake. So think about it. And the biggest piece of advice here is keep your loops as tight as you possibly can. And by tight, I actually mean not programming efficiency, but the number of lines. You want loops to be very easy to read, every line of them in one glance. So don't let them scroll pages and pages or even beyond a page. 5, 10 lines in a loop is really about as far as you should go. If you need to go more than that, then you should be breaking it up into subroutines so that you can actually look at each line and say, okay, I'm doing this, I'm doing this, I'm doing this. So what language should we be using for FRC? All languages have problems. There is no perfect language. And anyone who says, Python is the best, C++ is the best, Java is the best, LabVIEW is the best, yes, for certain particular functions that you want to do, yes, maybe it's the right language. But there is no perfect language. They all have warts, they all have problems. And probably the best thing to be guided by is, what do your mentors already know, or what are they prepared to learn in more detail? So the common languages, and yes, there are other languages you can use, but the common ones are LabVIEW, which is nice in that it's visual, so you can drag and drop and change values and so on. It's used in FLL, but if you're used to a traditional programming language, it's very, very weird. It's not a normal programming language. It's very powerful. I'm absolutely not against LabVIEW. I think it's actually a really good choice, but it's very weird for people who are used to text-based languages. Java, more English-like, but that's only English-like. It's not, you're not writing English, because English is an extremely imprecise language. It's quite verbose. C++ is potentially more efficient, and one of the big advantages is that the RoboRio and the coprocessor are using the same language. So there's library support for all of these languages, good library support for these. There's decent library support for some other languages. But the best thing is to talk to your mentors and say, what are you familiar with? What are we going to choose as a team language? But please choose a language. Don't have bits in different languages. That's just asking for trouble, because then people have trouble working out which language it's in, and debugging is different in each of these languages, and the environments are different in each language. So we still haven't really talked about much code. I'm going to get there, but I do want to talk a little bit about coding practice. Because even at FRC level, good coding practice will pay off massive dividends for how you work as a team. So divide the code into small tasks. Remember, computers are dumb. Go back to my first talk, remember your task list. What is it that you want the robot to do? What are your first set of goals? For example, in this year's competition or this year's game, getting off the starting line. So how do we get off the starting line? We want to turn the motors on. How long do we want to turn the motors on? We want to turn them on for enough to get off the starting line. So how big is that? We don't know. Let's practice. Let's find out. But let's assume that we turn it on for 2 seconds and let's see what happens. Okay, 2 seconds is too long or too short or whatever. Okay, we can modify that. Get that working. A really good programming practice is a short comment for each routine, which is a one-liner, maybe 2 lines, that is a short comment describing what the code is meant to do. That's what this block is meant to do. And that's not add 1 to this. Those sort of comments aren't particularly helpful, but ensure motor controllers are set to half speed. Okay. Now you have a description in English that you can read, and you can look at the code and go, does it actually implement what I thought it was meant to implement? Go back, implement that, check the comment and say, do the code and the comment match? Great. We think that's implemented. It may not be right, but we think that's implemented. Move on to the next section. One of the most frustrating things with languages, computer languages, is that there's a lot of boilerplate in almost all languages. The biggest advice I could give here is leave that boilerplate alone. Actually copy it verbatim from somewhere that has it already correct, because minor errors in the boilerplate can be annoying to find, and you actually need to know the language and the environment really, really well. And that's actually one of the most frustrating things I find. I'm quite familiar with these languages. Well, I'm not particularly familiar with LabVIEW, but I'm familiar with Java and C++. But if someone makes an error in the boilerplate or the include errors, it can be really hard to find where all of that is broken, because I don't know these libraries particularly well, and each environment is a little bit different. Remember, dumb typos, accidentally hitting a key on the keyboard, accidentally deleting things, are a fact of life. And this is where a development environment, an IDE, can really help, because it can highlight saying that include file references a file that doesn't exist. Therefore, the path must be wrong. or that function doesn't exist. So you've made a typo in the function name. The other one is to ensure that you have good coding practice of how you push and maintain code. Keep snapshots of all of your code. Every time you get to a useful point, which should be every meeting or every function implemented, take a snapshot of the code, ideally using something like Git or Subversion, one of the version control systems that allows you to keep a snapshot of the code, tag it, and push that to the robot. And then it's a really good thing to actually label the robot with the tag that actually says this is the version pushed to the robot. Then you can actually match up the code and the robot. And if you can go, this version doesn't do this correctly, it goes too far, you can write a new version that goes half as far, tag it, push it to the robot and go, okay, we can see the difference between these two tags. We've halved that distance and it now works correctly. And because computers are dumb and they'll do what they ask you to do, hopefully, write a test plan. What is it we're trying to achieve? Think about these tasks, and we talked about that in the first talk as well. Think about the tasks. How do we test each of these tasks? How do they actually, what are they meant to do? Do they do it? Have we finished this? Is it too hard for us? Do we need help? Are we going to create this as a stretch goal and think about it later? And inevitably, things don't work. Computers spend a lot of time not working. So the usual thing is, I don't know why it's not working. That's a very, very human reaction. But think methodically. So be methodical, come back and go, what is it meant to do? This is a really good time to work in pairs. So you sit down as a pair and you read the description. The description of this code is that this should happen. Now, this is the code. Does it match the description? No, it doesn't. Okay, we've probably found a problem. What does it actually do? And then you go, oh, instead of doing half speed, it's doing double speed. Add a comment that says why it's broken. Now go back and fix the code. Read the comment that says that it was broken and why it was broken. Read the code and say, okay, it's not broken in that way anymore. Read the original description that says it should be half speed and go, okay, I can delete that comment now because it should be matching the description. So keep the description comment, but not the bug comment. One of the most common problems when debugging code is reading what you think the code should say rather than what the code actually says. So read it out loud, and it's amazing how quickly we pick things up when we read them out, either to ourselves or someone else. And there's a lovely phrase called rubber duck debugging. So you can have a rubber duck sitting on your desk and explain the code to the rubber duck. If you can explain it clearly to the rubber duck and the rubber duck starts nodding, you're doing it well. Now, if you've got a partner, you can do rubber duck debugging with your partner. They probably will nod. The rubber duck tends not to. But their job is not to actually interject. Their job is just to listen to you explaining it. And if you're not explaining it well, they shouldn't say, don't you mean this? Don't you mean this? They should say, I don't understand what you're telling me. Tell me again what it is this code is meant to do. And then suddenly they can go, okay, I don't think the code is doing half speed. Let's look at that. And together you can go and go, oh, it's doing double speed instead of half speed. Act stupid, just like a CPU. Remember, it will do mostly what you tell it to do. And the final thing on debugging is assume that you have found a problem, not all problems. It's very easy to skip over a bunch of other problems once you've found that problem. And I know when you're rushing in a competition, there's this feeling of, oh, I found the problem, therefore I'll fix the problem, push the code, and we're done. It's really worth it, and it can be hard under competition pressure to go back and read the descriptions and say, does this block match? Does this block match? Okay, I changed this block. Now let's make sure it really matches the description. So I told you we'd look at some code. So let's look at some code. This code's on the web. That's just on WPI-lib. These are some sample autonomous or simple autonomous routines that drives forward for 2 seconds to half speed. It's available in Java and C++. The links are in these slides, but you can go to WPI-lib and it's there. And this is all WPI-lib robot.cpp. So this is C++. Doesn't really matter. The Java code looks like Java instead of C++, but it's not that different really. Note a lot of stuff in red. A lot of stuff in red on this code is not boilerplate. It's actually part of the language, but basically you just need to get this right by following examples. And in this case, you only need to fill in the routines that I'll talk about in a moment. Now, one of the weirder things with code, and there's really never been a good answer to this, is the bit that you care about first is the bit right at the bottom of the page where it says start here. And that freaks people out because they go, why am I reading? I have to skip all the way to the bottom before I can understand anything. Well, that's unfortunately the way languages tend to work. It's not really a good thing, but it's a historical way of the way code is written. So the first thing we care about is this routine called main. It's special in C++. It starts the application. And then there's some magic gobbledygook, return FRC, start robot, and so on. And that then starts off a robot. And we're going to walk through this code bit by bit. But this is the overall code structure. And I've cut out a lot of, this is a page and a half of code. And I've stripped down most of it because the major thing is this main routine, this robot class as it's called. And then if you notice, there are a number of routines in there. Autonomous init, autonomous periodic. They're the ones that start of autonomous and frequently through autonomous. Then there's teleoperate init and teleop periodic. And then there's also a test routine. And we're going to walk through each of those. So the first thing, and if you go back, if I just go back here, the link on that page there actually shows the full code, but I've stripped out some bits. So the first thing is the copyright block. This may not seem important, but it is actually a bit important. All code under International Copyright Convention is copyright. It's copyright to the author. And the only person who has rights to that code is the author. You need to add an open source license to allow other people to use your code. And without a license, you actually can't use someone else's code. So it's really important to put this license, and this is an open source BSD type license, and there are hundreds and hundreds of types of license. But the FRC code is under a nicely, fairly open license called BSD license. And the copyright just says, this is written by first. That's not particularly important, but more importantly, it's open source and it's granted under the first BSD license, which basically says you may do anything with this code as long as you include the references, which is great. That's all we care about. Then there's a hunk of boilerplate at the top. And as I said before, I think the best thing is to ignore, other than including it verbatim, this boilerplate, because I don't actually remember whether differential drive is under drive or under motors or whatever. I'd have to go and look it up and I'd have to go and find. And where's live window? Is it on the top level directory or is it under a subdirectory? Just use it straight out of an existing piece of working code. And that should be a block that you sort of go, do not touch unless you actually know what you're typing. Because if you change the capitalization of one of those phrases, the code no longer compiles. If you're using a development environment, it'll probably tell you, but it can still be annoying because you get all sorts of weird errors. So it's annoying boilerplate that is required as part of the language. It's a good idea to only include the bits that you care about, but there's actually not a lot of harm in including, it takes more time to compile, but there's not a lot of harm in including header files that you don't use. But just copy and paste it verbatim from other licensed codes. So I'm not going to talk a lot about what each of those mean, just that they need to exist. And each language is different in what those bits are. So we're going to get into the meat of the robot startup. So down the bottom, there's once again some interesting language features there. If not defined, running FRC tests call main is what that actually says. Doesn't really matter. Once again, this is boilerplate that you should just include as it is. But the highlighted sections in yellow are the bits I want to talk about. So the main routine does some magic to start up a thing called a robot. as part of starting up this class robot, there's an initialization routine called robot, which gets called a constructor actually in this language. And it does a few things at very first startup of the robot. So it does two things. It sets an expiration of 0.1. This is a thing called a Watchdog Timer. This says if the code doesn't tell the drive its status, or set the status of the drive, the motors, every 1/10 of a second, then something's going wrong and I'm just going to stop the whole robot. So this is the Watchdog Timer actually looking to make sure that you haven't caught an infinite loop. 0.1 of a second or 1/10 of a second seems like a very short period, but in robot time, that's a long, long time. You may have to increase that, but it's a good starting point. And then you start a timer. I'm not going to go into detail of what each of these does. I'm just trying to give you the structure of how things go together. So then back on the top page, back here, autonomous init. So the first thing was the initialization. The second one was autonomous init. And remember I talked about setting initial values. Although the timer is probably in a good initial state, calling a reset is a good thing. And in fact, you may be required. I need to look up the routine to see whether you need to reset first. But it's a good plan to reset the timer and then start the timer. Okay, so this guarantees that whatever might have happened before autonomous init, for some reason or other, the timer is guaranteed to start right now. It's reset and start. So that's as close as you possibly can to getting a timer right now. And then you have the autonomous periodic, and this is called by the main loop every so often during autonomous period. So what we're trying to do here, this is in line with the specification of the code, drive for 2 seconds. Note these comments that say what this block is meant to do. This is possibly a little too heavy on the comments, but when you're getting out early in code, writing these one-line comments that have a one-line implementation allows you to very easily say, oh yes, that matches, that matches, that matches. And as you get better at it, you might have fewer comments, but what we're trying to do in autonomous is drive for 2 seconds. That's a really good description. So how do we do that? We're looking at the timer. If it's less than 2.0 seconds, so timers are in seconds in this case, we want to drive forward half speed. So we're going to use arcade drive, single stick, and we're going to put some magic numbers in there. How do I know what those magic numbers are? Well, I now need to go and look up this function, arcade drive, and what it takes. And it actually takes a Y value and an X value, which is a little bit weird, but that's the order that it has. So whether it's the Y or the X, we're going forward. So we want to go the Y, and the negative just depends on how these motors are wired and so on. So negative is that way. And then otherwise, so if else, stop the robot. So our job is through the rest of autonomous, remembering this is called periodically. It's not called once, it's called again and again through autonomous. That's why there's this if statement. So the first time it's run, the timer has just been reset. So the timer is effectively 0. It might be slightly bigger than 0, but it's less than 2. So we set the motor to arcade drive minus 0.5 and 0. And then we exit because not reading the language, but in detail, not reading this code in detail, we fall out the bottom and then we get called again. And we keep getting called until such time as we hit 2 seconds. And at 2 seconds, we fall through into the else section and we stop the robot. So stopping the robot is turning off the motors. We set arcade drive to a Y of 0 and an X of 0. So that says we're done. And then until autonomous is finished, at which time the robot calls different routines, excuse me, the teleop routines are called. So teleoperate init comes next. At the end of, until the end of autonomous, it will do nothing. It will just sit there saying, don't do anything with the motors, don't do anything with the motors. And once again, this is going to be called many, many, many times until the end of autonomous period. So What do we have to do in Teleop? Well, what could we do in Teleop Init? We might want to reset the timer, for example. We might want to reuse that timer because it's not valid anymore. Or we might want the timer from the very start of the match to go all the way through. So let's say we're reusing the timer, we might want to do a reset and then start again in Teleop Init, which says we've now got a timer that starts at the start of Teleop rather than the start of the match. And you can decide, maybe you want another timer and you have a full match timer and a Teleop timer. That's the sort of thing that you might want to do in Teleop Init. You might want to set up other motor controllers and so on that you haven't used in Autonomous. Teleop periodic, once again, like the Autonomous, it's called again and again until Teleop is ended. So arcade drive, find out what the Y is, find out what the X is, and then drive. Okay, so it's arcade style with just one stick. And then there's a test routine, which I won't go into. This is just called periodically when you're in test mode. Remember back in that original piece of code, it said, if I'm not in test mode, call main. If I am in test mode, this gets called. It allows you to test things out without the motor action, without the robot fully running. And then there's a block of initialization. If you remember back on that original page, right down the bottom, there's an initialization section in the private. So this just sets up the motor controllers, sets up the drive type, sets up the console window, and so on. This is magic. And if you treat it like magic, you'll actually have a better time. Get bits that work, because this isn't really interesting, right? This isn't code you need to write. And you don't need to actually understand this in detail, other than I need to initialize these things in the appropriate way. And then you go, oh, okay, I need to add a third motor, for example. Oh, it needs to look a little like those ones. But this bit I don't want to change because these are my initial motors. And then the joystick and the console window, the driver station window. Once again, this is boilerplate. Try not to touch it. It might be a good thing to say, do not touch at the top and the end, and then you only add your code outside the do not touch bit until you're absolutely certain that you understand this well enough to change it. So I'm going to break some code, and then I'd like, Luann's sitting online, I'd like you to give me an answer of how the code's broken, and then give the answer in the channel to Luann, and then hopefully we can find out how I've broken the code. And I'm going to go through a number of these scenarios. And these are really common sort of mistakes to make. So how's this code broken?
So we're going to wait for some answers. I think people might be afraid to type in.
Okay, well, I'll tell you the first one. How long are we meant to be driving for? It's written at the top of this function, drive for 2 seconds. What's the next line say? It's checking for 3 seconds. So there's our first error. Instead of for 2 seconds, we're doing it for 3 seconds. And you might want to change things so that it's 3 seconds, but your specification of this routine, the comment above, drive for 2 seconds, now doesn't match the code. So one of those is wrong. So that 3.0 should be a 2.0 to match the drive for 2 seconds. You might decide later that 2 seconds isn't long enough and it needs to be 5 seconds, at which point you're changing the code dramatically and you need to go back and say drive for 5 seconds. And it might be a good time to say why you've decided 5 instead of 2, so that when someone comes along next week and says, oh, I thought it was 2, you can say, we made a decision to make it 5 instead of 2. And this is a good example of a thing you should have in your engineering notebook that says we found 2 wasn't good enough, it didn't get us far enough across. And because of our motor structure, we actually want to drive for a little longer. So there's another bug in this code.
So we have a comment. It says the speed is set to -4 on the x-axis, meaning the motor is also going backwards.
Yep. That's Y, I think, rather than X. But it's 0.4 instead of 0.5.
Right, and the negative would be just because of the configuration that you would have the motors actually set on the robot. Is that correct?
Which way the motors are running. So, you can fix that by working out how the motor controllers are going. Negative seems weird for that, but you need to draw a diagram of which way X and Y increase. Okay, but yes, that's the second one. So I'm going to skip on to the next page where I just highlight those errors. Okay. So we've got 2 there, and that comes back to my other point of don't assume you've found the problems, you found a problem. So if you change the code and fix that 3 to a 2, but you've left a 0.4 in there, it's not doing half speed. Does that matter? Maybe, maybe not. Maybe it's enough. Maybe it doesn't go quite far enough. But you can sit there fiddling both of them and actually chasing your own tail, because you think, oh, the motor needs to go for a bit longer, but actually if the motor went a bit faster, it wouldn't need to go as long. So those two might be in opposition to each other. So let's try a different breakage. What's wrong here? This one's much more subtle. Now you need to read this one very carefully. So I'm going to actually skip forward because this one is nasty, but possible. And it's unlikely to occur in the way that I've done it, but something close is easy enough to do. I deleted the else. The interesting thing is in some languages, and C++ is one of these, it's perfectly valid to have a block. So the thing delineated by braces anywhere, almost anywhere. So this says if timer less than 2.0, do the half speed, and then always set the motors to 0. So you're actually going to be, for the first 2 seconds, turning the motors on and then immediately turning them off. And then for the rest of the time, you're going to just keep them off. These are contrived examples, but these are easy things to do. You accidentally hit a delete key and delete the else, and you could spend ages trying to find that missing else. And if it's hidden behind a comment, for example, or underneath or just below the bottom of the screen, it can be really hard to find these errors. So keep a watch out for them.
So we did have someone who said the else is missing.
Oh, great. It's excellent. Yeah, the else is missing, and it is really subtle. And this is why walking through the code and reading it to each other would allow you to go, okay, I'm carefully reading it through and, oh, there's nothing guarding that block. That's really odd. We don't write code like that. That should be on its own line. And the formatting is also important. Notice that it's a good idea to have that laid out that you can see things clearly. So let's try a third one. Now I'm getting nasty. Actually, the else was a little bit nasty. What about this one? What's wrong here?
So one of the things we have to remember is that the YouTube, there's a little bit of a lag.
Okay.
So I think we need to wait for just an extra few seconds here.
Yep.
So while we're waiting, I have a quick question that has come up. Are these the sorts of things that you would typically see happening at Google? Like these are like sort of common errors that you would see, maybe not at Google, but at most big time software companies?
I think you'd see them at Google and any other similar company. Maybe not directly like this, but it is really easy, even for skilled, long-term professional software engineers, to accidentally comment out a line that's useful. to accidentally delete a keyword, but still pass the compiler. So if we go back, I won't go back because I don't want to take this off the screen, but that deleting the else, that's still perfectly valid syntax. And it's really easy to do that sort of thing. And I've had those sort of bugs in my own code, and it makes you feel so stupid. You think, how could I possibly have done that? How could I miss it? But if you actually carefully walk through the code, which takes a little time, then you go, hey, that's odd. We don't format code like that. There needs to be some keyword. Oh, there's a missing else.
So we have a comment. It says commented code where you want the code to work.
Yes, exactly. So if you look down, there's drive forward half speed, and then the line after, which isn't highlighted as a comment. It looks just like normal code. The robot drive, arcade drive line that we actually want to do something has been commented out. This is really, really easy to do, and it's really easy to do intentionally. Why do I mean it intentionally? Because you're trying to fix a bug. So you comment out a bit of code that you don't want to run at the moment for some reason. Like, for example, just after this, you have something that lifts the arm up, and you don't want to lift the arm up at the moment because you're actually trying to deal with the problem of the motor's going for too long. So you comment out the bit about lifting the arm up, then you push the code, you go to competition, you go, why didn't the arm lift up? Because you were actually concentrating on fixing the problem with the motors, but you forgot to put that piece of code back in. This is why code structure and code clarity is really important, because it's very easy for you to forget to put things back. And as far as the computer's concerned, that line doesn't exist. The compiler actually says there's nothing happening in this block, and it's perfectly valid to have an empty block in C. C++. Some languages don't allow you to do that, but it's perfectly valid here. So if timer.get is less than 2.0, do nothing. Otherwise, stop the robot. And that can be heartbreaking when you realize that you've commented out a bit that you didn't mean to comment out. A good practice here is if you're going to comment out a section, actually put some space around that section while you comment it out, so that it's sitting there right in the middle of the screen. So you go drive forward half speed, return, 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 comment out, return, 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 and you go, why are those lines sitting right in the middle of the page? Oh, that's right, I commented them out, I need to put them back. And then you delete the blank lines up and above. Normally you wouldn't leave too many blank lines because it wastes time trying to read the code, but that's a really, oh, I did something specific here, it's commented out for a reason. You could put a comment or just put some visual space there, and then when it's back as production code, you take the visual space away. Okay, there's your comment. So thank you to whoever picked that up. And one more. Okay. And I'll give some time to think about this one.
Yeah, so while they're thinking, one of the other things that I was thinking about when you were talking earlier about common types of bugs, and maybe you could comment on them, are boundary conditions.
Yep. I was talking with someone at work a while back. One of the best descriptions of these is called fence post errors. So there's two types, boundary conditions and fence post errors. Boundary conditions is when you're getting up to something and you need to stop somewhere, but the most common error is what's called a fence post error. Why is it called a fence post error? A lot of people don't understand or haven't heard the term, and once they've heard the term, they don't actually get why it's a fence post error. But once you've understood the term, you go, oh, that's so obvious. If you've got a section of fence that's got 4 fence posts, how many pieces of fence are between those fence posts? Or another way, if you've got 3 sections of fence, how many fence posts do you need to hold it up? And once you get that, you go, oh, that off by 1 error, that fence, that post that I missed or included is a really, really common problem. These come into code very commonly with less than and less than or equal to. So less than 2.0 says as soon as we hit 2.0, we've gone too far. Right? 1.9999999 is fine, depending on your resolution, but 2.0 is too far. But less than or equal 2.0 might allow you to go just that little bit further. And if you're doing integers, less than 10 means 9 is the last one. Less than or equal to 10 is 10. And that's where these fence post errors come in, or boundary condition errors.
All right, we have some answers.
Yeah.
So the first one says else code again. And then the next comment is it never stops. It's an endless loop.
It's not quite an endless loop because it's being called by the main routine and it's during autonomous. So at the end of autonomous, this won't ever get called again. So it's not quite an endless loop. But yes, the first it's close, but the first answer is also correct. There's no else condition. So what's going to happen here is if the timer is less than 2.0, we set the arcade drive as we did before, but we have no else condition. So we've set the motors going, but we never stop them. So for the rest of the time of autonomous, the beyond 2 seconds time, we're not doing anything. So they will actually be set at minus 0.50 for the rest of the time. And then, bonus question, what's going to happen? Let's say autonomous is 15 seconds. So what's going to happen?
While we're waiting for a couple of answers here,
Yep.
I'd also sort of like to hear your thoughts on test plans in terms of what can you actually be testing before you have a robot?
So I think that comes back to the task list. What are the tasks that we want this robot to do? So for example, the first task is get off the start line. What's the test plan for getting off the start line? The robot needs to move forward half the length of the robot, for example. Let's assume we're sitting halfway on the line. So how do we move half the length of the robot? Well, what's half the length of the robot in centimeters or whatever? How fast do we need to go to do that? So the task is, okay, 2 seconds should be fine. We'll actually, once we've built the robot and put it on the field, let's see if 2 seconds is plenty, just not enough, or way too short. So your test plan might be, do we comfortably get off? And so your test for that feature would be, do we get off the start line? Yes, good, pass. Do we not go into any foul condition? So we must get half the robot off, but we can't go more than 20 robots long, or whatever it is, whatever the distance is to the other end of the field. It's more than 20 robots. So that would be your test plan. And then when you actually put the robot live with the code, you go, okay, let's test that routine and only that routine, which is the autonomous. Okay, it moved forward 2 robots lengths. Is that fine? Yes, it's off the line. Great, passed the first condition. Did it go into a foul zone? No. Could we do less? Could we do more? That's a different decision. You could say two robots lengths is clearly far enough. It's off the line. And if something happened to get in the way, we've got a good chance of being well off the line. Or you might go, this actually interferes with our teams, the other members of our alliance. And it'd be better if we only went 1 robot, which is clearly more than half, but it doesn't get us way into the field where the other robot that can do more in autonomous wants the whole field to play. So you can think about those sort of limits there.
All right, we have an answer. The answer is penalties.
Penalties.
Uh-huh.
Yeah.
That's all we got.
Yep. So yes, you've probably driven all the way to the other end of the field, or something else might happen. Remember way back in the first slide that we were talking about code, there was a watchdog that said that the motors have to be set every 0.1 of a second. We're not doing that. Right? At 2.0, we stop going into this block. So for the next 0.1 second, at 2.1 seconds, we haven't set the motor speeds and directions. Therefore, the watchdog is probably going to kick in and turn us off. That's why we have watchdogs. So if we forget this piece of code or we accidentally comment it out, we're actually going to be stopped. But assuming that the watchdog wasn't there, dangerous not to have a watchdog, yes, we drive right to the end of the field and we'd be in a penalty zone. So you see the swings and roundabouts there. It's nice to have a watchdog, but you can see that it can cause you problems. Okay, so yes, we forgot to stop the motors. Whoops. Once again, easy to do. What happens if we commented out mrobot drive arcade drive? Same thing, we were testing it and we were going, okay, we actually want to go slower for a while. Let's just stop them for a moment. Whoops, we kept going. Okay, so there are some examples of bugs that we can introduce into the code. And as Luann asked, is this the sort of thing that you see in professional companies? Absolutely. We're not very bright as human beings. We get things wrong. This is a lot to keep in your head. There's a lot of boilerplate, a lot of bits of code, areas that you need to comment out, changes you need to make. And it's very easy to accidentally do something. And this doesn't make you stupid, but it can make you feel stupid. And the way to get out of that is to stay calm and be methodical. That comes back to what is the code meant to do? You've got that comment at the start of the block that says, you know, turn the motors on for 2 seconds at half speed. Great. Or move forward half speed for 2 seconds. Does it do that? So it's really tempting to go, oh, it's not working, bash, bash, bash. Is it working now? No, bash, bash, bash. Every time you push the software to the robot takes 30 seconds or a minute. You could have saved that time by sitting and looking at that minute, looking at the code to go, oh, actually it doesn't. Because every time you push the code to the robot and it's still broken, you're getting more and more frustrated. Whereas if you sit there calmly going, does it do what we said it was going to do? You're much more likely to pick up the problem. And then you do one push and you go, yes, and it did what we want. Great. Read carefully. Once again, we're humans. We tend to gloss over. We tend to read what we'd like things to say rather than what they actually do say. So read them carefully, use your rubber duck or preferably use your teammate. And try not to both work on it at the same time. There are advantages to working on code together, but when you're doing debugging, it's a good idea to have one person that actually says, this is what the code is saying, and the other person is listening. And if the person who's listening says, it's not correct, they shouldn't say, fix it like this. They should say, I don't think it says what you thought it said. Read it again. Oh, it says 3, not 2. Yes, good. Okay, how do we fix that? And then together you fix the problem. And then you go back and you read the description, check the code, and move on. Stay calm. Debugging is stressful. Debugging brings out our natural I'm an idiot reflex. And the I'm an idiot reflex is not very good for getting things fixed. And we all feel like idiots when we see bugs in code. You're not an idiot. You've just made a mistake. These things happen. And it's very easy through a simple typo or accidental leaning on a keystroke to make a mistake that actually causes you a problem. So stay calm, walk through it methodically. And most of all, why are we doing this? We're doing this to have fun. So have fun. So I'm going to stop presenting and give us time for questions.
So we'll see if any questions come in.
Sure.
I guess while we're waiting to see if any questions come in, I'm also curious, is there a like how many lines of code would a typical programmer write in a given day or a given week that you would expect to be fairly bug-free?
So I think bugs per line, if you're doing one better than one bug per line, you're doing well. No, seriously, all code is buggy. All code without tests is broken. And we haven't got into testing strategy and things like that. That's more advanced. But you know, I'm a very strong proponent of what's called test-driven software design, where you actually write the tests first and you write the code to match the tests. That's hard to do in the FRC environment, but it is possible. But thinking about the description of the code and the implementation is good. Programmer productivity is a really, really hard thing. It depends on the language. So some languages are much more expressive. 5 lines of Python is probably far more expressive than 5 lines of C++, typically. Now, with templates and things like that, that's not necessarily true, but it's typically true. Are there advantages to writing in that language versus another? Yes, but the productivity is a problem. But I have seen programmers who write upwards of 5,000 to 6,000 lines a week, which is phenomenal. And I've also seen incredibly productive programmers who generate 50 or 100 lines a week, but they are good lines and they've thought about them and they've said, this is what we need to implement this problem. That doesn't seem like a lot of productivity, but they're writing good, clean, bug-free code. So lines of code is not in itself a good measure. Frustration, I think, is actually one of the biggest measures I had as a team lead and a manager. Do they feel like they're actually being productive? Whereas if they're sitting there beating their head against it, no matter how many lines of code, they're probably not writing useful code because they're sitting there going, ripping it out and trying it again. And that's a non-answer.
That's okay. We have a couple of questions.
Yeah.
The first one is, how do you set code style standards?
So which code style standard doesn't matter. That you have a code style standard is important. And one of the big things, and in fact, the Google code standards are available on the web. I wrote, or I was a co-author of one of the code standards, but the code standards are basically stop arguing about this, right? You are wasting time arguing about code standards. So the best thing is to, as a team, go, this is our coding standard, that's it. So for example, I'm not a big fan of braces at the end of the line. I used to actually prefer the braces on a separate line, but the code standard in many companies is brace at the end of the line. So I changed to braces at the end of the line because that's not important. And if you have a team that's going, we're going to have braces at the end of the line, no, we're going to have them on the next line, you're wasting time that you could be writing code. That stuff is not important because the compiler doesn't care where that brace is. It can be 27 lines down as long as there's nothing in between, right? And if you want to blow your brain, go and have a look at the obfuscated C contest for some really amazing code that is totally unreadable, but perfectly valid. But readability comes first. So I suggest go and pick a code standard. And I think the Google standards are pretty good, clear, compromise standards. So think of those. Many other code standards have come out, but just pick one and say, this is our code standard. We're done. Let's not argue about that. And that's the biggest advantage of a code standard, is to just go, we're not arguing about code standards. This is the code standard for the team. Let's move on.
Okay. And we have another question, which is, do you recommend coders to build robots and builders to code?
Yes. I believe everyone in an FRC team should be comfortable with electrics, mechanical, and code to a reasonable extent. You're going to have people who are better at one or more suited to one than the other ones. But I think everyone on the team should be familiar with each of those areas to a greater or lesser extent. And one of the best things, if you are sort of mechanically minded and not code minded, changing that other part of your brain to understand a bit of the code actually allows you to understand the robot better. And it says, oh, you've designed this great arm, but I can't actually write software that gets this arm adjusted properly. It's really hard to do because think about the code to do it. It's difficult because I've got no sensor. So how about we go back and add a sensor that actually works out, or a limit switch or something like that. And you go, oh, okay, if I have a limit switch, as soon as the limit switch goes off, the arm's high enough. Right? I don't have to write this complex loop that actually determines whether it's, so many centimeters off the ground. I can just have a limit switch. And by getting that both hardware and software view, you go, oh, we can simplify the design by making a bit more hardware and a bit less software, or vice versa. So yes, I think everyone should learn the basics of each of those three areas.
All right, well, it looks like that's all of our questions. I want to say thank you so much to Gordon. This was excellent tonight. Looking forward to the next time that we can welcome you back to talk more about something FRC related. I also would be remiss if I didn't thank Project Bucephalus, who've been helping out with the chat and making sure that everything runs smoothly tonight. So big thank you to 5985. They're there every single week working on this behind the scenes. So huge thank you to them. And I guess we'll see you all next week.
Okay, well,
Have a good
thanks.
night.
I hope this has been useful. Please send comments my way if you think things should be improved. And we'll talk later. Thanks.
Bye.